Okay, good morning. So today we're going to talk about the PA systems. This is the network cabling class, and during which the 14 weeks of this course span, we are covering things that have to do with the telecommunications business, but not the type of telecommunication in a sort of original understanding, which would be radio or amateur radio or radio frequencies and antennas. That's the different type of telecommunication. That's the original meaning of that. I call this the modern type of telecommunications, which evolves around data and other things like sound systems, intercom, telephone systems, and security alarms, nurse call systems, fire alarms, and things like that. So today we're going to cover the PA systems. During these 14 weeks, I'm going to give you the essence of what you might encounter if you get a job in this field. And PA systems is one of them. The PA systems, they branch off in various ways. There's a different type of, public address, which is basically sound systems. It could be anything from the couple of speakers at in the ceiling at your local KFC, fast food, or it can go as far as the good old rock, what I call it, the good old rock and roll stage setup. Then churches, arenas, conference rooms, conference systems, and school PA systems, home theater systems. Wow, it's you can make a good living, or you can actually maybe write a PhD material just on the sound systems, and that thing never ends. As one of my friends says, that blues song never ends. All right, here's my radio voice. Okay, so let me bring it to the full screen. Whoa. All right. So PA systems, public address. And today we're going to concentrate on something that's called a constant voltage system, which is very popular, not known to everyone, just a regular bread eater, as I say. Might not know this type of sound system. Usually, when it comes to sound systems, our understanding is, home stereo, popularly called home stereo, which is something that's called a receiver, which is basically an amplifier and some sort of a receiver built into it, and a couple of speakers left and right. Or maybe a surround system if you want to go fancy with it. So you got left, right, and the center, and you got left, right, rear speakers. Or maybe if you want to get really, really fancy, you're talking about $6,000, $10,000 plus, sometimes $30,000, $40,000, $50,000 if you want to get into home theater system. Some people like to do that, and there are companies who concentrate on that. So that's as far as our imagination goes when we talk about sound systems. However, there's a little bit more on the commercial side of the moon, right? That's the other side of the moon. So we're going to talk about that. It is when it comes to this type of job, this field of work, these systems are extremely popular. So it's just impossible that we don't cover that. We have to cover that because there's too much money to be made if you know what you're doing, and there's too much money to be lost if you don't know what you're doing, right? All right, so let's go. So public address, PA system stands for public address, and this is a two-part class. First part, it just so happens that we have split, kind of a blended setup this semester, this summer semester, summer 2024, actually, if you watch this thing 10 years later. So we have two classes. One is online, and there's another class the same week, which is in person. So all those classes online are recorded, and all those classes in person, you're going to get your notes and those post-it notes, post-it lecture notes, and you're going to have to make your own personal notes when you're in class. All right, let's go back to that PA system thing. All right, PA stands for public address. Basically, it's stands for sound system. I just put a couple of pictures here. Well, there are a couple of differences. Well, the main difference is the type of loudspeakers. Right? A loudspeaker is basically a speaker. Right? It's just a technical term for a loudspeaker. This here is, well, kind of a speech stage setup. If you want to do a little bit of a, bingo event or any kind of a public speech. So it's a good portable system. Or some people use that when they are performing, in local bars. So there could be a guy with a guitar, singing some songs. Have a quick setup, not too many cables, not too many pieces of equipment. Quick setup. Start performing, get the cash, and put it, tear it down and put it back in the trunk. So that would be this type of setup, in the simplest terms, would serve a nice closed room setup. Closed room setup, which means it has 4 walls, ceiling, and a floor. A gym, a classroom, a bar, things like that. All right. Excuse me. All right. So now here, if we go to the left of the screen right here, we also have some sort of amplification system, some sort of a mixing system. So this here is very similar to that end, right? And over here we do have some microphones or sound sources, otherwise sound sources. And over here we do have, well, just a microphone. And that's pretty much all you want with this type of system. What do you see here? This here, instead of the loudspeakers in enclosures, or sometimes called columns, we have something that is, we have horns or paging horns. This would be typical setup for an outside, and because there's a microphone here, and so that is, that it's a hint. Right? It's good mostly for just voice. Can you pump some music through it? Yeah, but it's going to sound like it's going through some sort of a funnel, and it's not going to sound very pleasant. Although some people do pump some music through that. The way the speakers are constructed is that these here are designed to be in a closed room with the phenomenon in mind, which is, in an enclosed room, most of the sound that gets to your ear gets reflected from the walls, ceiling, floor, furniture, and anything that is in there. Most of the sound that gets to your ear gets from the reflections, not in the straight line. Yes, there's some sound that goes in a straight line from the source to your ear, but most of the sound that gets into your ear gets from the reflections. Outside, you don't have the reflections because it's an open space. Soccer field, football field, school yard, or whatnot. So the speakers or the loudspeakers are constructed in somewhat different way, because most of the sound that gets to your ear from the like if you're outside, because there is nothing to reflect from, although maybe some buildings or whatnot, right? But in the open field, there's nothing to reflect from, so you have to rely on the fact that most of the sound has to be in a straight line. So the shape of the sound reflector or projector has to be done in this way. And usually those paging horns The general rule is somehow, for some reason, the further you stand away from it, the better it sounds. If you get really close to it, you won't be able to stand that. Right? So here's that, there you go. One picture is worth 1,000 words. We haven't gone past the first slide yet, have we? All right. Okay, let's go to this second slide. PA system, the purpose and description. Public address system is an audio system consisting of audio sources, amplification equipment, and output transducers, such as loudspeaker. Purpose: to process, amplify, and distribute audio signals or signal over a large area. Okay, so we got that. Okay, this slide was short. We remember this this diagram of the basic concept of any telecommunication system. So we have input transducer. We know what transducers are, right? Transducer is, just as a reminder, a transducer is a device that converts one form of energy into another. For example, a microphone. Microphone converts the sound, the air, longitudinal wave vibrations into electrical signal. Right? So that's a transducer. Right? Then we got a transmitter, link, receiver. We know that from previous class, right? So let's put some meat on these bones. All right, input transducer when we're talking about PA systems, well, it would be a microphone, MP3 player, guitar, any kind of other instrument. That would be the input. Right? Transmitter, there'll be a preamplifier, mixing console. Hey, telephone system as well. We'll talk about that too. Right? But not today. All right, and then there's the link. Link, copper cables. For the most part, we can use some fiber optics, and we also get wireless links. And the wireless link would be analog. Well, wireless, all these could be analog or digital. And we expand on that a little bit further down the road. Receiver, well, audio amplifier, that's pretty much it, and maybe some processing equipment. And then output transducer, and that usually would be some form of a loudspeaker. It could be the enclosure or a paging horn, or it could be earbuds. If you have something like on stage, it's called an in-ear monitor system. This is for the artists to be who are on the stage to hear back what's going on, because the speakers are pumping the sound from there forward, so the only thing that they can hear is a bad reflection from the wall, and they won't be able to perform. So that's why we have something that's called wedges, like stage monitors, which are the speakers that are on the floor pointing at the artist so they can hear what's going on. Or sometimes it's also a very popular system. It's called in-ear monitoring system. Sometimes you can see on TV artists wearing some weird kind of earpieces that are, they're huge, covering the whole inside of the ear. And sometimes they're nicely decorated or whatnot. These are the in-ear monitors. They completely separate the outside of the ear from the inside of the ear. So if that thing is turned off, you wouldn't be able to hear much. Well, maybe some vague sounds here and there. But then there's a whole team that works on the whole mix, separate from the front of the house. In front of the house is the public, to the monitoring system. So there's a separate mixing person or a crew that takes care of just for the mix for the artists on the stage. And these are called in-ear monitors, which is glorified version of earbuds. All right, now where do we see, in which environment can we encounter some kind of a useful PA systems? Well, here, school, church, theater, meeting rooms, sporting events, retail stores, stage, hearing impaired. Hearing impaired is for people who need a little bit of assistance of hearing. Then that system could be parallel in with the main sound system, and sometimes it's just that there's no front of the house. public events, shopping malls, and wherever you can imagine the sound system can exist. You can install this for your own use, or you can install this for somebody else and cash the check. All right, definitions, keep going here. All right, here's a bit of a disclaimer here that I have encountered over the years that I was in the industry. Here, just so you keep that in mind. I'm going to read that. In written installation contracts, the language might differ. And that applies not only to this, it applies to pretty much everything else. Always confirm the definitions for every contract. Just because I give you some definitions here, it doesn't mean that somebody 5 years from now, from some company somewhere, it doesn't mean that they watched my presentation and they're going to stick to the definitions that I gave, right? Some of that thing might vary from one place to another, but we got to start somewhere. We got to give, I have to give you some sort of basic ground knowledge, right? All right, so for example, the sound system used to amplify rock concerts is commonly called the PA system or simply PA. While technically it can be called sound reinforcement. So here's a sound reinforcement. What's a sound reinforcement? Well, it's reinforcing the sound, okay, and in various ways. Sometimes you want to reinforce it a lot. Sometimes you want to reinforce it just enough to be understood. And some of the good conference systems are set up in a way that people don't know that the sound system is on, but everybody can understand everybody. When you know that the system actually is installed, if somebody pulls the plug and the sound system goes off, and then there's that bit of a confusion going on. Why can't I hear what the other person is saying? Right? Because some of the distance could be 10, 20 feet, 40 feet. But I digress. All right, so sound reinforcement. Any system which amplifies one or more sources for a live audience. Okay? All right, now I have three bubbles here. One is the public address PA, sound reinforcement, hearing impaired. Okay, let's take a look at some of those here. Public address PA system is used for public announcements, background music, and what I call good old rock and roll stage, theater, church, arena, and such. Right, that's my favorite, and such. All right, now sound enhancement. The sound enhancement would be meeting rooms, conference environment, and I would also include the theater here. It depends what kind of a setup you're doing. Depends what kind of approach you take. Sometimes sound enhancement is just the right thing to do on the theater stage. Talk to me if you're interested in that type of stuff, or maybe you have done some of that stuff and you want to share the experience. I will share my experience with you. I want to talking about sound enhancement. All right. Basically, that's what it is. For meeting rooms and conference environment, or theater stage, the idea is that there is some sort of a general carpet coverage or cloud coverage of microphones, with the microphones, coverage of the room, or coverage of the area where the speaking takes place. So if it's a conference, like a city hall meeting, there will be one long table at the front with a bunch of people sitting at the table, and in the audience there will be a bunch of chairs for people to to participate in that meeting. Yeah? So the microphones can be hung over that big table that people are speaking, and sometimes the microphones could be concealed just to not distract, because the whole thing is the purpose of the meeting is what is being talked about, not to enjoy the sound system, right? So that's the idea. And the microphones are amplifying the sound that they're picking up these are overhead mics. They are picking up the sound that's happening at the table and reinforcing it towards the public seats just enough that the whoever's sitting in the public seat, they understand nicely and clearly what's being said at the table. If you turn the system off, you wouldn't be able to hear, or you'll be able to hear that somebody is saying something, but you wouldn't be able to make out what that person is saying. So that's a properly set up sound reinforcement. There are there are a little bit more details involved when it comes to that, because the further you get away, the sound travels 1,000 feet per second roughly. So if you have a bunch of speakers overhead in the ceiling over the public seats, then every so often you have to separate the bunch of speakers that are hanging over top, and you have to put them on a delay, right? Because if you're if you're talking to a microphone, the signal travels quite fast, almost instantaneously, right? And this, because sound travels 1,000 feet per second, it takes maybe a couple of 3, 4, 5 milliseconds to get to your ear in a straight line and from the reflections of the walls. So you would hear the sound in the speaker first, and then a few milliseconds later, you would hear the sound coming from that person's mouth. It is very annoying. So the purpose of the delays is that, when people are sitting further away, is to slow down the electronic signal, introducing a delay, so it matches with the latency of the signal that's coming from the person's mouth to the other person's ear. Right? So that's and sometimes depending on the distance, sometimes you need 1, 2, or 3 different delays. So you need 2 or 3 different amplifier channels. Yeah. Hearing impaired, which is audio enhancement, quite widely used in churches. Aside from the main sound system, people do come with their own hearing impaired devices, or sometimes the hearing impaired devices are being distributed for the people before the service. People bring their own earbuds maybe, or sometimes yes, sometimes no. It's a very popular system for that. Also, it's a form of hearing impaired system. It's the thing that I mentioned a few minutes ago, the stage in-ear monitoring system. It works in the same way, except the hearing, in-ear stage monitoring system is a little bit more complex, because there's a whole mix involved, a whole team of people could be involved in that. All right, so that's as far as that. Now, with this thing here, I'm just going to go back to this thing here. Whenever you get a contract or tenders written or any contract written, please confirm terminology, because what you understand by somebody saying something might not be something that somebody meant. Yes, we all speak English, and we should stick to the basics of the basics, but just to make sure, because sometimes there are some differences of in understanding by from one person to another. Always confirm things that are written, not just the when it comes to sound system, but everything else. All right, this brings us to something that's called a constant voltage distributed system. All right, let me bring something up here. Oh, come on. There you go. There you go. All right, here is a blank space. Let me just get some better color. Okay, and pencil. Do I get nice lines? Okay, good. All right, let's say you have a home stereo. Here's the amplifier, and here's your TV. Okay, I'm just going to put a little bit of a rabbit ears antenna, and here is your TV. All right, now if you want to enhance the sound system, you would get some sort of an amplifier, And you'll get some speaker here. You get some speaker here. This goes here. That goes connected to here. And usually, in this case, the speakers would have something that's called impedance. That would be 8 ohms, usually. Right? Now, in some of the bigger stage gear, huge stage gear, sometimes you can go to 4 or sometimes 2 ohms. Right? But generally, that is, the 8 ohms is the speaker impedance. I also have a whole presentation. We're going to take a couple lessons later on what actually impedance is, because we're going to talk about something that's called impedance and also something that's called characteristic impedance. But in order for me to explain what characteristic impedance is, I need to explain what impedance is. In some subjects, in some classes, you probably have touched on that subject anyways. But I'm going to give you my spin on that because it's part of this this class, and I'm actually happy with that one. So, okay, impedance. Impedance is in short, the resistance to the electric current. However, the impedance also considers the alternating current, because alternating current behaves a little bit different and affects different devices a little bit different way than a constant current, which is DC or direct current. All right, so here 8 ohms, no problem. The output of this amplifier is also 8 ohms. All right. And over here, so we get the match of the impedances. This here and this here, they are equal to each other. And because the impedances are equal to each other, we get something that's called a maximum power transfer. So the system is quite efficient. All right. Actually, I'm not going to erase that. I'm just going to set up a new page. All right. So let's see. We have a, well, restaurant, school, bar. Let's take a school hallway. We have somewhere there, there's pencil. Somewhere here, oh, come on. Somewhere here is we're going to have an amplifier. And here's a symbol, general symbol for an amplifier. Here's the input and here's the output of an amplifier. Okay. Can you hear the rooster in the background? Yeah. All right. Now let's say there is a hallway somewhere. No? Okay, good. The thing doesn't stop. Here's a hallway that goes straight and, well, and turns right a little bit. Okay. All right. So let's say the output of the amplifier is 8 ohms. And this hallway would have speakers. I'm just going to draw circles. All right, we have speakers in the hallways just so the sound can be distributed properly. All right, what is the problem that already happens here? All these are 8 ohms. Every single one of those speakers is 8 ohms. Well, from the DC theory, you know that if you have a resistor, let's see, that's a resistor. I can do a better job. Here is a resistor, and here's another resistor, and you connect these two, and you connect that to an ohm meter. If this is 8 ohms, I'm not going to write the ohm because it's going to take too long. If this is 8 ohms and this is 8 ohms, how many ohms are we going to have if we connect them in series? Well, 16. That's right, Charles. We're going to have 16. Okay. Well, 1, 2, 3, 4, 5, 6, 7, 8 times 8. That is going to give us 64 ohms. If we had this scenario, if we connected them in series. Oh, that is not good, okay? Because here's the output, 8 ohms. Here's the difference here, 64 ohms. Those two impedances, the total impedance of that is not equal to the output impedance of the amplifier. Well, we don't have maximum power transfer by far, which means there's power losses. And if there are power losses, somewhere, somehow that power has to go somewhere. And usually it dissipates as heat, and it can damage the amplifier or it can damage some other equipment. No good. Right. Well, so what is the other situation that we could have with these two 8 ohm speakers? We can connect them in parallel. All right. Can connect them like this. And what are we going to have? If this is 8, if this is 8, we're going to have 4 ohms if we connect it to in parallel. Because when you connect the loads in parallel resistances, and if they are the same values, you just get that value and divide by the number of devices. So in this case, we get 8 divided by 2. If we connect 2 more of those, this is 8, this is 8. 8 divided by 4, we're going to get 2 ohms. Okay? So the more you connect, the less total resistance you're going to have when it comes in parallel. Why? Because even though you're adding the resistances, you're still providing another path for the current to flow, which means every resistance that you add is going to be less than the infinite resistance of the air, somewhat infinite resistance of the air, which means you're gaining one more path which is less than infinite. The current has easier time to flow, so less resistance. So in parallel, the resistance, total resistance, is going to be less than the smallest resistor that is connected. Well, let's say here we have 2 ohms. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Oh, right. If we get 8 of those speakers, we're going to have 1 ohm of the total resistance of that. And here is still on the amplifier, we have 8 ohms. Again, these are not equal. And 1 ohm is almost like shorting the speaker, the amplifier output to the ground. That thing is going to heat up so fast, and it's going to go poof. The smoke is going to come out. So how do we connect that so it's nice and efficient? Well, you could have 2 ways. One is very efficient, and the other one is a little bit less efficient. But it could still be done in a pinch if it's not too big of a system. Well, let me bring up another. If we have 2 resistors, these are 8 ohms, these are 8 ohms. If we connect them in parallel, the total resistance of these two is 4. Okay, then we do the same thing again. We connect those. Here's 8, here's 8. So here's 4, here's 4, 4 plus 4 is 8. You still have, now you have 4 speakers of 8 ohms, and you still get 8 ohms of the total impedance or resistance, which can be connected to the amplifier, which its output has 8 ohms. So you get maximum power transfer from the amplifier to the whole array of the speakers. Can it be done? Yeah, it can be done. Have I done it before? Yes, but not. You can't do this thing if the system is big. Well, if you have a school, for example, here's a hallway, here's a hallway, all right, here's a hallway, all right, and here's the main kind of a hallway there, and there's some other hallways branching out, and every hallway has maybe 20 speakers here and 20 speakers here, maybe 15 speakers here. Can you do that, the serious parallel combination, with that many speakers to accomplish 8 ohms on the total, as a total impedance? Yes, you can, but don't. It would take you forever to come up with 8 ohms. And if there is any slightest change that you make, you throw the whole thing out of balance, and you're going to have to redo the whole thing. And when you have to come back, there's a bunch of wires in the ceiling. What's connected to what? No, it's not efficient system at all. Now, if you have a small store that, oops, that you have 1, 2, 3, 4, 5, 6, 7, maybe you have 20 speakers or 25 speakers in a relatively small area. So here's like a store, and there will be a cash register here, and here's the main door or whatever. And over here, that would be something like, I don't know, 20 yards or 20 meters here, and maybe 15 meters here. That's you can get away with that. I still wouldn't. I still would try to do the other way that I'm going to show you, but I just wouldn't do it this. But if you really have to, because the owner, sometimes you get those small private contracts, and they're cheap, and they just don't want to, So can you do this thing? So you explain, yes, we can do that. I'll do it once, but if there's something that goes wrong, just so you know, it's going to take a longer time to figure it out. But hopefully nothing is going to go wrong, so the decision is yours, right? But if something goes wrong, I don't take the responsibility, and if I have to come back, it is going to take longer time to troubleshoot. And usually they say yes or something like that. It's not my favorite way of doing things, but still, sometimes I get my arm twisted, and I will just do that. Right? Now, before I let you go today, and we're going to go to the other system we're going to cover is the other way. It's called the distributed constant voltage system. I'm going to leave you with one interesting concept. Where do we have that? All right. Here's a website that I just got 5 minutes before class. I just was kind of overlooking the presentation and said, oh, what else can I give them, right? Faraday's law of induction. And here's the website, just so people don't say that I infringe some copyrights. Here's the reference, data forth, okay? And here is the address. So the reference is provided. I'm all legit. Faraday's law. What does it state? Faraday's law of induction says, Whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called induced current. Okay, we ran out of space there. Okay. But before I do that, so here's the interesting thing that we're going to use to our advantage when doing something that's called a distributed audio system. The CCW and the CW stands for clockwise and counterclockwise when it comes to winding. So it doesn't matter in this case, but this diagram just shows that. Here's the voltage, input voltage, and here is the load. I'm going to leave you with some concept here. Based on that Faraday's law, if a wire, let's say copper wire, is placed in changing magnetic field, then the current is going to start flowing through this wire according to the changes of the magnetic field. It also works the other way. If you have a power supply here with alternating current, and if you have a wire, if you have a straight wire, not even a coil, that straight wire is going to produce a magnetic field around it. However, if it's just one single straight wire, yes, we can notice the magnetic field around it, but we can't use that too much. We can't make too much use of that. So that's why if you have that wire, and if you go back, if you have the wire, and if you go back and put a little bit more beside it, 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 and so on, all the magnetic fields are going to add up. And the more you do that, the more wounds you get, the more buildup of magnetic field you're going to get. So this coil is going to produce a magnetic field, which sometimes we call a flux. And flux is the effective magnetic field. So it's going to produce lines of magnetic field, right? From north to south. It's going to create a magnet. If you insert a ferrite, which is like iron type of a stick inside that, right? It is going to make that magnetic field travel easier. It's just going to provide, because the magnetic field likes the metallic objects there too. It's going to make that magnetic field stronger. But you don't have to. You can have it without the metal stick in it. It's still going to have some. So you provide an AC voltage here that is going to create a magnetic field, and the magnetic field is going to go up and down, up, because the voltage goes up and down, up, left and right, left and right. The current flows that way, left, right, just ever changing, right? Which means that magnetic field is going to change. It's going to go this direction, and it's going to go that direction, and it's going to go this direction and that direction. Same, to actually see the to accommodate the current. So it's going to be ever changing all the time. Right? Well, according to the Faraday's law that I just gave you, If you have another wound, another bunch of windings, and the reason why we do windings is to kind of add those wires there, so the effect of that Faraday's law is multiplied. Then that magnetic field is going to be passing through those wires and is going to be changing up, down, left, right. And so it's changing, because if the magnetic field is just not changing, if you have a magnet and you put the wire beside it, you're going to have no current flow. But if you just keep, from your physics grade 12 kind of thing, if you just wave a magnet, permanent magnet in front of the wire, close to a wire, you're going to make current flow through the wire. So because this is changing here, so it goes left, right, it's just sometimes very fast, 60 times per second, sometimes even more. It is going to pass through that wire, which is going to, this is the input, and it is going to create a voltage. And if you connect a load to that, you're going to create a current, which is going to be the same as this current if the number of the wounds is the same. Here's the primary winding, here's the secondary winding, and if the number of the wounds of the primary winding is the same amount of winding, same amount of coils, then the current is going to be the same, 1 to 1, or the voltage is going to be the same, sorry. And if the voltage is the same, the current is going to be the same. If you have twice as many here in the primary as there, so this is like, let's say this is 1,000 wounds, and let's say this one is 500 wounds, then the voltage induced on that is going to be same as the ratio. So it's going to be 1 over 2, half of that, because this winding is half of that, and this winding is twice as much as that. So the voltage is going to be proportional. How do you say proportional? There. To the voltage, primary to the secondary is going to be the same, or proportional to the voltage, which means the current is going to go down, I1, I2. Why? If the voltage here is twice as much as the voltage here because of the number of windings, here is 1,000, here is 500. If this is 100 volts, if this is half of the amount, it's going to be 50 volts here. But the current is going to be smaller here than here. The current here is going to be bigger. Why? Because transformers transform voltage, then transform current, but they keep power. The power here, the power dissipated in this system has to equal to the same power dissipated in this system, or the availability of the power. Transformers transform volts. So if you raise, because power, remember, we're almost done, guys. Power equals voltage times current, if you are considering something that's called RMS values, root mean square, true power. We're not going to get into the complex numbers of the, because, impedance and all that. So in order to keep the same power, if you increase the voltage, you have to decrease the current, or if you decrease the voltage, you have to increase the current. There is another thing that the transformers can transform, and it is the impedance with the letter Z. So the transformers transform voltage, they transform current, they transform impedance, they keep the power. And that is the idea that we're going to use to our advantage when we are going to produce something that's called a distributed system, constant voltage, because you see here, these are the speaker connected all in parallel, but these are not the speakers, just the speakers. These are speaker stations. Look, there's a transformer here connected to the output of the amplifier, low impedance, which is 8 ohms, transforming that into high impedance, so there's not too many windings and there is many windings here. Low impedance, high impedance. And the voltage that is connected to all the speaker stations, and the speaker station consists of a loudspeaker and a step-down transformer, which is in parallel connected to the output of the step-up transformer, because stepping the impedance up from low to high. But then it has to be stepped down from the high to low, because this is 8 ohms and this is 8 ohms. By using the transformers like that, we can use that effect that I just explained to you to our advantage, that we can do. We can connect this type of a system here. We can connect that in this way. Look, you just connect them, tap them in parallel, and the transformers are going to work it out between each other on how much to take and how much to adjust the impedance matching thing. So the sound system is power efficient, and you can just keep adding the speaker stations as long as you don't exceed the total consumption of the power that the system is able to provide. But that's going to be the next class when we are going to see each other, I'm not sure, sometime later this week, and that's going to be the in-person class, and we're going to explain that. We do have the setup, all those speaker stations that are in our lab along the walls. That's it, that's this system here. So you can play with that. I can show you what to do if you want. We don't have a lab this summer semester that has to do with that, but if you're interested, which I encourage you that you would, I'll show you how to do this, how to work it out. All right, so that's it for today, and we're going to finish it off. Unfortunately, there won't be a second part online recorded because the second part is going to be in person in class. Okay, see you guys later, gals. Have a great rest of the week. And remember, what day is it? It's almost Friday, because every day is almost Friday. Because every day is almost Friday. Yeah, there you go. All right. Thank you, guys. See you. How do I end this thing?